thank you very much for having me at first. Thank you very much for inviting me to share some of my research on dark data, which I think is very fitting for the scope of this workshop. So maybe let's jump right in. So yeah, we live in the zettabyte age. That means like we produce tons of data. So numerically, these are at the moment, we're somewhere, pointer doesn't work, okay. So somewhere on at 188 zettabytes, that means 188 times 10 to the power 21 bytes. That's a very huge number. You usually cannot imagine such numbers, but yeah, you can do comparisons, but it's a lot. And maybe it's an IDC estimation. And of all that data generated, there's lots of data that I or others would call dark. What is dark data? We will check in a minute. But as of now, I think everyone has already some picture in mind because like dark data is a strong metaphor. So we have these like 188 zettabytes of data in total worldwide. And of this data, IDC says that 80% of data is just dark data. Bjorn has also some numbers on it. They say that like more than 50% of data are dark, and over 30% of the data is redundant, obsolete, or trivial, or what they call rot data. And just 14% are business critical data that really can be used for a good purpose or for some purpose. Okay, these are now pure numbers. Let's at first see generally how data is produced or where large amounts of data come from. And of course, as I'm coming from the sciences, I will have like an example where big data is really generated. For example, in high energy physics, there are these particle accelerators where they let particles crash into each other. But it's not just that experimental device. It's a supercomputer attached to those particle accelerators calculating the traces of particles. No one has ever seen a Higgs boson particle, for example. It's like a calculation that there must be a particle somewhere done by these supercomputers behind the accelerators. And also some numbers again. There are like, when such an experiment is running, there are like 40 million collisions per second. That means like 15 trillion collisions per year. And each collision produces like 1 megabyte of data, making 2 petabytes per year just by this experiment. There are lots of more experiments there, and so on and so forth. So just that you see that in these, in places like CERN and others around the globe, lots of research data is produced. Of course, not all of this data is stored. Some is right away thrown away, but lots of it is stored. And in science, we speak of the fourth paradigm of science, like that we're now in an age where we can produce huge amounts of data, and we can also analyze huge amounts of data because we have the storage capacities and we have the processing capacities, and we can search for the needle in the haystack in the huge amounts of data. Whereas in former decades, we had computer simulation that is kind of a mix of empirical science and theoretical science. And it could generate data, but not to an amount that we're doing today. And also in this book where this paradigm is like defined, there are already problematizations of that. Like Tony Hay writes that, so what I mean by the data iceberg is that there is a lot of data that is collected but not curated or published in any systematic way, which is already a pointer to that what I call dark data later. And of course, but I'm not an expert for these kinds of data, but of course I want to mention it anyways. So in public and private data, we kind of find the same problems. So because these visions of the Internet of Things, where we equip every device with a microchip and a connectivity to the internet, and then things can happen like, why is my LG washing machine using 3.6 gigabytes per day? Just to mention, it's not clear. Maybe there has been a hack of the washing machine and some Bitcoin mining. But in principle, with this example, you see that devices like washing machines can now be used to generate data in big amounts of data, and that's really an interesting thing. Of course, this is related to cloud computing. We have to store this analyzed data somewhere. It's in the cloud, which is of course also a metaphor. It's stored in data centers actually. And of course, big data and AI, with its in principle endless feedback loops, produces, uses, and analyzes huge amounts of data. And an example is the smart city. These numbers are a bit outdated from 2016, but I'd just like to show here that different parts of a so-called smart city produce lots of data, where some are transferred over networks. So we've now seen some example of data, and first of all, before I now will go into details with dark data, I will have a short disclaimer. Like in the following, I will mainly talk about dark data as they appear in science. However, much of the conceptual framing can also be adopted for any other forms of data. Not all, but some. In the following, I will mainly talk about dark data as something unwanted. And you can also imagine cases where you want dark data, where you want your data to be hidden and obfuscated and dark, for example, for privacy reasons. When there's health data involved, you don't want it to be understandable for everyone, maybe. And this is an interesting type of data, like the toxic data, which we will hear about in Jan Krasny's talk, which I'm pretty much looking forward to. Dark data is not to be confused with the dark web or the dark net. And because sustainability also comes in the title somewhere. And for me, it's not only energetic sustainability, it's also scientific sustainability. So not doing the same task twice, or the same study twice, or the same experiments twice, because like in that Large Hadron Collider setting, it would cost you lots of energy, money, whatever, resources. Okay, so let's go into the topic of dark data. The term dark data was initially done by someone from Arizona, information scientist from Arizona, Peter Hydorn, who associated dark data with removable media. So an example of dark data is the type of data that exists only in the bottom left-hand desk drawer of scientists on some media that is quickly aging and soon will be unreadable by commonly available devices. The data remains in this dark desk drawer, inaccessible to the scientific community until the scientist retires. So some research was done, and we store some results on an USB stick, and we put it somewhere in our desk drawer, and we forget about it. And if a colleague comes by and asks, hey, do you have that data of that study? Yeah, maybe I have to look it up. It's somewhere lost. We all know that with the USB sticks, where they go and where they roam. And of course, you can typical what happens after the publication of results in science. So soon after the publication, specific details get lost, and then general details about the data collection get lost. And then comes some critical points, like if there are accidents that destroy your media, or especially if there's a career change or retirement. So usually the person who is responsible for the data, you ask the person usually, hey, what did you do in that study? Do you have the data? They leave for whatever reasons, and they take all that mental storage with them. So these are two interesting, for me, kind of groundbreaking work in that research direction. And for me now, the notion of dark data is a bit broader. That means it's not only that data on the removable media that is roaming around somewhere, it's all that data which is undocumented or not commented, so you can't understand it anymore. It's all that data that is unavailable or hidden, like on the USB stick, which is not managed or not curated, which is unstructured, and even that data that is selective or statistically biased or erroneous. So in principle, dark data is all the data that is not usable and or not accessible, and it is not fair. I don't know who of you have heard about FAIR principles. I come to that later. And of course, dark data is usually neither sustainable nor minimal. And these data, these phenomena on some data items have certain implications, especially on responsibility, then epistemic problems, ecological problems, economic problems, and legal problems. I will mainly focus on the first three of them. So let's get into it. So unavailable data. So I was working at that high performance computing center. They have these huge supercomputers there, 25 petaflops of performance and 42 petabytes of disk storage on some 2,000 hard drives and stuff like that. I worked 10 years and I was actually technically also administrating the tape archive system. So where selected data gets archived for long-term storage, and so tape media, just a quick hint that tape media is still the media to be at data centers. So also Facebook, Google, for their cold data, they all use tape storage. It's not outdated. Some of us think of the old VHS tapes for movies, which are outdated, but not for as a storage medium. It's still the state-of-the-art medium. And all these data centers have this tape archive systems as a back-end storage, as a long-term storage. And I was administrating that system. And yeah, and I found interesting things because I read that dark data was a very fitting definition, and I did a study on that tape archive system, and I discovered that there was kind of lots of dark data. So that was data on the storage system which hasn't been associated with any active account anymore. So the accounts were already deleted, but the data was still there. So what to do now with the data? Should we delete it? Can we delete it? Should we publish it? Can we ask the person, do we still have the contact to the person? So you see that there is an ethical problem how to deal with the data once you identify it as dark data. And of course you can say, yeah, 2 petabytes, not great, not terrible. And nowadays it's not that much, 2 petabyte, but yeah, it's still money and energy that goes into that data. And yeah, maybe you should handle it differently. And this was an interesting finding I did there. And I guess it's like that in many data centers, which I'd love to make a study about, but of course they won't grant access. Yeah, so here you see that there can, yeah. You delete the account, but not the data that is associated with the account. The account is just entry in a database, and if you don't have like clear policies at the beginning where you state that after 3-month period they are deleted, please care about it. And this was actually the case, and now there are such policies that prevent data. But this is partly data that's 20, 30 years old, and none of these policies were in place. And I guess it's also the same in other data centers. Okay, so another and a very extreme example of dark data is the example of the Challenger disaster, where the space shuttle was launched and one of the sealing rings on the solid booster tanks was inelastic, and it got the spaceship exploded like 70 seconds after start, and all crew members died. And I've taken that example from a very interesting book by a statistics professor from London, by David Hand. He wrote a whole book about dark data, but only about the statistical dark data, like biased data, erroneous data. But it's very interesting. So, and that book pointed to that example, and I find it very enlightening. So, what was the problem, and how does it relate to dark data? I don't know, some of you might know the story, but the thing is, I already told about the sealing rings. So there were lots of talks at the engineers at which temperature to launch, and they were presented like test data of that sealing rings, where the number of incident and the launch temperature in Fahrenheit was shown, and they were just presented this data. And I would ask now someone, at what temperature would you launch to minimize incidence with the sealing rings? You would maybe claim something like, yeah, maybe around 50 or lower. And actually that was the case. And of course there was political pressure. USA wanted to have a launch quickly and stuff like that. And then we had this problem that was exactly the wrong temperature to launch. So, and the thing is, the complete data set, if you would have seen the complete data set, it would have been a complete different story, because at the complete data set, there would have also been the launches or the flights with no incidents down here. And with that in mind, I would come to another conclusion. Maybe I would focus more on a region at higher temperatures. But this was just the data that was presented. And so there was like an selective data during launch preparations. And the claim was that the low launch at low temperatures is safe. And the correlation that the sealing rings became inelastic at low temperatures was not seen. The launch was done at 2 centigrades. And the other thing we've heard already, that it was exploded. So what's the story behind it? So that example shows that there can be an epistemic problem when dark data is involved. And of course, not all of them lead to disasters like these. It's a very extreme example, but maybe very concise. So it's not clear what we can know from dark data sets. So if the data is selective or biased. And it's not clear what knowledge claim or action we can derive from this data. And the main question, maybe also interesting for this workshop, is how minimal can the data set be not to lose their significance? So of course you want to minimize data, but you can't minimize it in a way that it loses its significance. Okay, these were like the responsibility implication and the epistemic implication, and now I would spare some words on the ecological implications. Like there is a study here from 2022 where they explore the sustainability challenges with respect to dark data. And we see a steady increase in power consumption on the global carbon footprint of data centers and communication networks. And you can here, for example, see that the global footprint of the ICT sector has almost doubled from 2010 to 2020. So going from 1.8 to, or more than doubled, sorry, to 3.7%. And this is, of course, because we store everything now on cloud, and storage is basically quite cheap. But of course, it's the business model of data centers, or commercial data centers, to give you like the possibility to store everything in a cloud. Every picture we blow up via instant messaging remains somewhere in the cloud, for the most messengers at least. And they did this study, and they used like the Vanson Byrne categorization in dark data, rot data, and critical business data to show it, like how many carbon footprint, land footprint, and water footprint is consumed. I will just skip that. You have that in the slides if it's interesting for you, but it's like relating to that 50, 30, and 14%, according to the numbers of Vanson Byrne, of course. Okay, so we talked now about the problem. So what is the solution? Basically, the solution is data management, or in my field, research data management, of course. So we need a rigorous data management coming from like that data handling, that after generation and evaluation and publication, data is somewhere put into private files or moved into Thresh and whatever, to a data management where after the generation, evaluation, and publication of data, we ingest everything in a system which is granting open access for re-evaluation, and of course leading principles for this are open data and fair data. I mean, I think open data, most of you know. Who of you has heard of fair data already? Okay, so very few. Okay, so I will do some words on that. So, and this is about it. So research data management should avoid or reduce dark data and instead create fair and open data. And of course, part of this is making data sets minimal. So the embedding of open data is in open science for the sciences. So it's one of the pillars here next to open source, open methodology, and so on and so forth. And open science is a vision of global, open, and sustainable science. It's been already supported by many political decision makers like European Union, UNESCO, USA. And sustainability or sustainable science here means that science should be transparent and traceable, reusable, and to avoid duplicate work. I will now just go. Okay, and here's the memorandum from the UNESCO on open science, and they specifically mention that it should include thinking about ecological consequences and think about sustainability. But let's talk about just open data here, because this is maybe the most important. So open data means that for any purpose, the data may be used, disseminated, or reused with licenses like CC licenses and so on and so forth. And fair data means that data should be, it's like the acronym, findable, accessible, interoperable, and reusable. Fair only makes statements about the quality of the data with regard to reusability. That means fair is only a paradigm to make data reusable. It does not have to be open necessarily. And open data only makes statements about the open usage of data. And statements about minimum sustainable data sets are only implicit here. And maybe some very quick words on FAIR, as so it's a principle that was introduced almost 10 years ago. And these are generic principles that can be used as a guide for good research data management, or even for data management in general. They define the what, but not the how. Like the data, what should it be? It should be findable, accessible, interoperable, and reusable. Then it's good data, it's high quality data, and we're doing good research data management. As they are generic, they must be defined for each specific area or activity. They're not a standard, and often fair enough is sufficient. Sometimes you can't fulfill all those. But in the scientific community, there's a definite consensus to use them. At least in Germany, I just speak for Germany, of course. Yeah, the essential thing about is that research data must be identifiable and provided with metadata to achieve that. And the principles are here. You can read that. We won't discuss it here. And you have the pointer to the publication where it's in. Okay, so what are the implications of fair and open data, especially with regards to the topic we have in our workshop here? So open data guarantees that there is data openly available, okay? And therefore we don't have to reproduce the data. That's of course quite trivial, but I wanted to list it here. And open data, according to UNESCO, at least should also consider ecological principles and efficiency. And for me, both are a pointer to data minimization. And fair guarantees that the data will be findable, accessible, understandable by third parties, and hence reusable. And all of this here helps, of course, diminishing dark data, because we do something to lift them out of the dark, where it's not available, it's undocumented, it's hidden, it's biased, towards something that we can really use on purpose. Okay, so I'm almost at the end of my talk. So just a few words on the implementation of fair and good data management, and of course, against dark data. So you should, or we are always saying we want to be compliant with the good scientific practices that have been formulated. And for us scientists in Germany, it's the guidelines for safeguarding good research practice from the DFG, German Research Foundation. And what is really important is establishing your data lifecycle. So think about what is done in each phase of the so-called data lifecycle. So data lifecycle is somewhere an orientation. So you start creating data maybe, or maybe use it from a prior phase, then you organize and store it, then you use it or analyze it, then you maybe share it, reuse it. And interesting point for me is, of course, always when it comes to archiving or destroying the data. And when you define a specific data lifecycle for your data, you always it always shows you possibilities for intervention. In what part of the cycle you do what with the data to make it to ensure quality and not to make it dark. And especially for that, archiving or destroying, decision criteria is really important. And we did this, for example, for that high performance supercomputing data. So we did this, so we balanced like relevance and volume of the data. And so we said that for all the data that resulted in a publication, for all that simulation data that's behind the publication, and in the publication you maybe just see a graph, a simple graph, but there's lots of calculation and data behind it. So for that data, of course, the publication with the plots must be preserved, and that's already done by the publishers and the libraries. But more interesting is the stuff below, like for us, especially the input, the code, and the analysis results are important, because with the input and the code, you can recreate the experiment if needed. So that must be stored. Selected simulation should be stored, and what not should be must not be stored is like unsaved simulation restarts, test runs, and so on and so forth. Similar holds for if that data did not result in a publication. It may be worthwhile archiving anyways. So like input code analysis results should be, if really important and needed, selected simulation results should be or can be, and the others should not. But I think this is really important for any data. You should establish clear decision criteria when to keep and when to throw away data, and if you keep it, what or how to handle it. Okay, so do I have time? Really? Okay. So just a quick one. NFDI, German National Research Data Infrastructure, is a big German national project of doing all this, like developing a national research data infrastructure in Germany, developing an overarching research data management and increasing efficiency of science. And it's a key role in German's digital strategy. And yeah, that's maybe can skip that for the sake of time. And they are organized bottom up. So apologies that some parts are in German. I didn't find an English picture here. So each scientific domain has one or more of these NFDIs, and the researchers themselves should think about, for me as a physicist, it would be good to have that, and that, so I can handle my data better. And then all the solutions should somehow emerge. Let's see how this works in the end. But you see there, depending, like NFDI for health is for health data. NFDI for memory is for historical sciences. I work in MARDI, Mathematical Research Data Initiatives. And there are interesting cross-sections where dark data is discussed in the ethical, legal, and social aspects group. Yeah, so basically, this is the end of my talk now with a quick summary and conclusion. So dark data is a manifestation of poor data management, and we've learned about some phenomena and some implications of dark data. And they are estimated to definitely more than 50% of the global data volume. And the CO2 footprint is like 5.26 million tons per year. I've spoken to environmental researchers. They said it's not huge, but it's something you can always work on. The small things are sometimes easier to work on. There are effective principles and measures for sustainable data management, like fair and open data. And minimizing data sets is always an important task to diminish dark data. However, as already said, we need to balance minimum data or the need for minimum data while preserving the significance of the data. And however, dark data will become a major problem as data production still rising, and data storage is super cheap compared also to computation. And let's see what future brings. And yeah, thank you very much for your attention and for having me again.